Hello, good morning to everyone. I am Tariq Jamil. I'm a student in Ghulam Isa Khan Institute of Engineering Sciences and Technology, Pakistan. Today, I am going to present my work on deep ultraviolet light-emitting diodes. The title of my presentation is Upgradation of Aluminum Gallium Nitride-based deep ultraviolet light-emitting diodes internal quantum efficiency with step decrease aluminum indium gallium nitride-based electron blocking layer. Let's to briefly explain the title of my presentation. So we actually enhance the optoelectronic performance of deep ultraviolet light emitting diodes just with introducing step decrease quaternary electron blocking layer. With step decrease, I mean that we actually decrease the aluminum concentration in each layer in quaternary electron blocking layer. In today's presentation, I will simply explain the basic concept of light emitting diodes, the basic problem in the development of light emitting diodes, or motivation in proposed study. So what is light emitting diodes? Light emitting diodes is basically a semiconductor devices which work on the photoluminescence principle. Here two different type N and P type semiconductor material used. From N type semiconductor material, electrons come to recombine with holes in a specific region that we call depletion region or active region, and the recombination of hole and electron is the result produced energy in the form of photon. So this is the band diagram of light emitting diodes. This one is the conduction band, while this one is the valence band. From the conduction band, electron comes to recombine with holes and a result photon release. This one is the basic schematic part of light emitting diodes, in which this one is the n-type layer. N-type layer means n-type semiconductor material, while this is the p-type semiconductor material or p-type layer, and this one is the active region or depletion region. The energy and wavelength of the emitted photon depend on the Planck's equation E equal to hc by lambda, where E is the energy of emitted photon and lambda is the wavelength of that emitted photon. This one is the basic sketch of light emitting diodes, while this one is the modern or complicated schematic of light emitting diodes. In modern or complicated schematic, electron blocking layer and engineered depletion region are introduced. The purpose of electron blocking layer to suppress the electron effectively, while in the engineering of the depletion region with the quantum mills and quantum barrier to maximize the recombination or recoupling of hole and electron remarkably. So we engineer the depletion or the active region in modern or complicated LEDs. There are many problems in the development of efficient light emitting diodes. One is the electron leakage. As we know, the electron having lower effective mass, so for the electron it is easy to overcome this potential and recombine with holes in this region, and there is the non-radiative recombination release. For the hole, as we know, the holes having higher effective mass as compared to electrons, so for the hole it is difficult to overcome this barrier. The another problems create from with the phi doping. As we know, when the aluminum concentration in aluminum gallium nitride increases, the activation energy of magnesium increase, and when the activation energy of magnesium increase, the phi doping problems occur. The highly threading dislocation density also one of the main problem in the development of LEDs, which arises from the mismatches of Fe layers polarization induced. The phi doping problems, electron leakage and hole blockage result uneven distribution of carrier. So we are motivated and inspired to overcome the electron leakage, facilitate the hole transport, and optimize to receive optimized carrier recombination in the active zone in the LEDs. For this, we proposed a LED. We actually engineered the electron blocking layer, as I mentioned in the title. So we introduce the quaternary electron blocking layer. Quaternary means we incorporate the indium composition in aluminum gallium nitride, and with the stepwise decrease the aluminum concentration by 10% in each layer. We divide the 12 nanometer electron blocking layer into 6 layers, and in each layer we decrease 10% aluminum stepwise. The overall parameters of our proposed LED is similar to the reference LED. Then we simulate these two devices by the STR package silence, and with the help of this we receive very interesting result. The first one is the energy band profile of both LEDs and the effective barrier height in the proposed LED increased by from 328 millielectron volt to 436 millielectron volt. It means the proposed LED have better capability to confine the electron in the active region or in the quantum wells. Similarly, the effective barrier height for the holes in the proposed LED decrease from 340 to 328 millielectron volt. It means the proposed LED facilitated the holes transportation to the active region. Similarly, the electron and the holes concentration simultaneously increase in the proposed LED, and when we calculated it numerically, the electron concentration increased by 30% while the hole concentration increased by 45% in our proposed LED. When the electron and the hole concentration increase, it means the radiative recombination will also increase in our proposed LED, and when we calculated it numerically, the radiative recombination rate increased by 337%, which is very huge number. And similarly, the internal quantum efficiency of LED, which is a main parameter for the optoelectronic performance of LEDs, increased by 37%. And interestingly, the proposed LED is nearly pre-efficiency group. This improvement is assigned to the step decrease quaternary electron blocking layer. This quaternary 3-nitrides material have very interesting feature. The first one, the indium in this material work as a lubricant for the holes to facilitate the holes transportation to the active region. The second one, the aluminum indium gallium nitride and last quantum barrier decrease the lattice mismatches, which alternatively induce the polarization field, and as the result for the hole to overcome the barrier easily. Similarly, the aluminum indium gallium nitride have higher conduction band offset, so for the electron it is difficult to overcome the effective barrier height of electron blocking layer. We investigated the effect of quaternary electron blocking layer on the optoelectronics behavior of deep ultraviolet LEDs. The results indicate that our approach improved optoelectronic performance of deep ultraviolet LEDs remarkably. Based on these results, we highly trust that this approach provides a fruitful guideline to the researcher for achieving efficient deep ultraviolet LEDs. And we or this numerical study, we collaborate with Riken in Japan, and soon our result will be confirmed experimentally. I would like to thank all the organizing committee of International Conference of Energy, Water and Environment 221 and sponsor for arranging this conference and providing me opportunity to present my work. I would like to express my sincere and deep gratitude to my research supervisor, Engineer Dr. Mohammad Usman, for their kind and encouraged behavior throughout my MS study. At the last but not the least, I special thanks to Ghulam Isa Khan, Institute of Engineering Sciences and Technology for awarding me graduate assistantship and STR group for technical support. Thank you so much. Thank you for listening. Welcome to any comments.